Mining has a long history of employing large machines. Some of the largest machines ever built were designed for surface mining. Some of them are still in production. Others have perished with time, and hardly any of their remnants are left behind. But there is a gigantic beast that is now in sleep, yet standing as tall as it used to be during its glorious working days, the Big Brutus. In West Mineral, Kansas, United States, there is a mining museum that is the home of this giant rope shovel. Every year, around 22,000 to 30,000 people visit the Kansas plains to see this 16-story tall engineering marvel. And it is, so far, the world's largest electric rope shovel in existence. Currently, the largest rope shovel available on the market is the P&H 4800XPC. It stands 73 feet tall and has a 50-foot long and 49-foot wide upper house. With its 92 cubic yard dipper and payload capacity of 135 short tons, this largest operating shovel of the current time can fill the world's largest dump truck in just a few passes. On the other hand, the Big Brutus is much heavier than the P&H 4800XPC, with a total weight difference of 3,847 short tons. It stands taller with its 160-foot-high boom. Its machinery house is 79.5 feet long and 58 feet wide. But interestingly, this behemoth has a 90 cubic yard dipper with a payload capacity of 150 short tons. It is so large that you can park a D9 dozer in it. Despite being larger in every dimension, the Big Brutus could carry just 15 short tons more than the uncrowned largest operating shovel of the current time. This highlights the changes brought about by technology, as well as the various demands of today and possible concerns in the future. But what led to manufacturing such a large machine in the past? And why don't equipment manufacturers produce larger shovels when the technology is way better than before? Presently, mine owners prefer cost-effective solutions over large mining machines. Climate change and automation technologies are also changing the mining sector significantly. In the last 150 years, the mining sector has seen many changes. In 1964, mining was very different from today's mining practices. Mining companies wanted more production, and equipment manufacturers were in a race to design and assemble larger machines. It led to the manufacturing of many giant machines for mining that were the largest of their kind and the largest in the world. The very first generation of rope shovels was run by steam engines. At that time, coal was the primary source of harnessing energy. In the late 19th century, the electricity network expanded over many states. Access to electricity for commercial and domestic users significantly increased the demand for coal. As a result, a new race started between companies to build more and bigger units of mining equipment. In the United States, the annual coal production was only around 50 million short tons in 1875. It went above 678 million short tons in 1918. Meanwhile, Bucyrus, a pioneer mining equipment manufacturer based in Ohio, became famous for its steam-powered rope shovels. Those first-generation shovels weren't just confined to mining, but they were also used for mega construction projects. The 51-mile-long Panama Canal, through which cargo worth $270 billion moves every year, was dug out by the Bucyrus steam engine rope shovels. Steam engine power shovels featured a fixed mast and swinging boom, similar to a quarry derrick. A bucket was linked to the end of a dipper stick positioned on the boom. The boom was lowered to allow the bucket to dig an arc through the cut face, then lifted and swung to dump. Manual swinging and dumping involved a man on one side of the shovel hauling a rope to swing the boom back and forth, while the guy on another side used to tip the bucket. The shovel was powered by a vertical boiler to drive a double-drum chain hoist. These shovels were moved on railroad wheels. Bucyrus helped pioneer the use of electricity as a power source as far back as 1917, though conventional electric motors weren't suitable for shovels. In 1919, Bucyrus invented a new DC electrical power system, which is known as the Ward-Leonard Motor Speed Control System. This motor speed control system became standard on all electric shovels. The Big Brutus had the same technology. In fact, its original name given by the company was Bucyrus Erie Model 1850B. Two 3500 HP electric AC motors mounted in the center of Big Brutus were connected with their respective DC generators via a shaft. These motors run at a constant speed and transform AC electric power coming from the grid into mechanical power for the DC generator. The combined AC motor and DC generator is known as the genset. By feeding the produced electric power through a network of variable resistance devices, the Big Brutus was able to control the speed of its main motor. Overall, the Big Brutus had 13 gensets that were used to power 8 hoist motors, 3 swing motors, and 2 crowd motors. From digging out to discharging the mining material, the Big Brutus was capable of completing a digging cycle in 1 minute. But to perform just one digging cycle, it used to take 7,200 volts. According to some estimates, this rope shovel had been using more energy in a day than could run a city of 15,000 people. Empire District Electric Company was responsible for supplying 3-phase electricity to this gigantic shovel. From the supplier to the P&M substation, the electricity was transmitted by overhead lines. Then, the P&M company had a network of utility poles and a 4-inch diameter ground cable. From the substation to the shovel, it was a 2-mile power transmission line. A cable handling machine is deployed behind the rope shovel. It has a cable reel to feed or retrieve cables when the rope shovel moves. Other than the cable handler operator, a team of 3 men was required to control and operate the Big Brutus. They included a shovel operator, a groundman, and an oiler. The shovel operator sits in the cab of the Big Brutus to control every dipper digging and shovel swinging of the machine. The groundsman on the ground had the duty of guiding the shovel operator when the shovel had to move backward or forward. Lastly, the job of the oiler was to maintain the oil in all the hydraulic systems and make sure they kept working properly. Operating such a giant was difficult, but building it was even more. It took almost a year to build this monstrous machine. First of all, they build a cribbage by cutting large timbers and laying them down like a building structure. Then, they lifted and placed lower deck components on the cribbage using a heavy-duty crane. This was done to integrate the lower deck components with the undercarriage later. For instance, they welded 4 hydraulic cylinders under the lower deck. They will work as the legs of the shovel and leveling devices. Later, these hydraulic legs were connected to the undercarriage truck. The Big Brutus consists of 4 undercarriage trucks. Each truck works as a separate unit of wide tracks, and each rectangular pad of the track weighs around 2,000 pounds. Every truck could be moved separately because each had 2 dedicated 300 horsepower motors. After assembling all trucks of the shovels, they were crawled under the lower deck, using electric power to weld each with one of the installed hydraulic cylinders. In this way, the undercarriage gets connected to the upper body of the shovel and becomes capable of standing on its own feet and maneuvering itself. But this monster could travel at a speed of 0.2 miles per hour. Moreover, the undercarriage is so big that a man standing between the upper and lower tracks cannot be taller than that. The track system can only move the shovel back and forth. To revolve on its own axis, the Big Brutus needed a swing rack. Like a giant cog, a swing rack enables the machine to rotate the upper house horizontally along with the boom and dipper. For installing the swing rack of Big Brutus, it took a team of welders who have been working day and night to build this giant cog in 3 shifts. One after the other, each heavyweight component was lifted, placed and assembled to complete the Big Brutus. This includes the upper section of the shovel, which houses critical components known as the housing. After installing the main machinery, such as motors, hydraulic pumps, electric systems, etc., they had to cover all sides of the housing section with side house panels. It had been 6 months since the assembly process began, and the workforce was now dealing with winter snow. During this time, another team was working on the assembly of the boom. They had to attach the assembled boom to the A-frame of the shovel. For this purpose, they erected the boom with a crane and used high tensile wire ropes. Now, the dipper stick needed to be integrated with the saddle block. A dipper stick allows the rope shovel to push the dipper forward while cutting and take it back while loading. The forward movement of the dipper stick is called crowding, whereas the backward movement is called retrieving. Instead of using the crane, they hoisted the dipper stick using the boom of the rope shovel. Then, they connected it with the dipper stick. On the day of its birth, Big Brutus was welcomed by many miners who came with their families to witness this enormous beast in action. The site where Big Brutus was deployed had seams of bituminous coal at varying depths, ranging from 20 to 69 feet deep. The Big Brutus was needed to remove the upper layer. This upper layer is known as the overburden, and the process of removing the overburden to obtain the valuable ore is called strip mining. Before initiating the digging process with the Big Brutus, explosive holes were horizontally bored into the strip pit wall. This rotary drill was able to make a 5-inch diameter and many-foot-long hole. Subsequently, the explosive expert fills with explosives and then detonates in a controlled manner to soften the hard rock for the Big Brutus. Then, this coal monster starts removing the overburden. With each bite, Big Brutus was able to scoop up 90 cubic yards or 135 tons of earth. Furthermore, in just 60 seconds, Big Brutus could extract the overburden below ground level and pile it up to 150 feet high. Once the overburden was removed from the stratum, a dozer with a ripper was used to pull out the coal layer. Next, the coal was excavated with a smaller shovel and loaded onto dart trucks. This coal was obtained for local electrical power generation. Those dart trucks take the coal to a facility where it is refined for power generation. The refined coal was then transferred to the power plant via train lines. Big Brutus operated for 11 years, from 1963 to 1974, removing overburden from approximately 9 million tons of coal. However, this $6.5 million powerhouse was built to serve for more than 25 years. At the time, Pittsburgh and Midway Coal Company had several challenges in operating its mining activities. These challenges included rising competition from other mining sites in Kansas that caused a reduction in the price of coal. An energy crisis led to an increase in the cost of electricity. The last monthly electric bill for Big Brutus was $27,000. Moreover, strip mining raised climate concerns among the people. They started to oppose the extraction of coal. The change in mining trends not only shut down the mining site, but also retired the Big Brutus too early. Pittsburgh and Midway Coal Company tried to sell Big Brutus, but it was too large to be moved anywhere and too costly to continue its job. In 1983, the Pittsburgh and Midway Coal Mining Company donated the machine to Big Brutus Incorporated, a non-profit organization of local individuals interested in the preservation of this rope shovel. This monument is still there, telling a magnificent history of the past and the people and machines that worked along. With that, we conclude this video. Hope you find it informative Before you go, let us know your thoughts about Big Brutus in the comments. Share, like, and subscribe, and we see you next time.